This lesson, Lesson 17, examines various advanced topics related to column buckling. This includes local buckling calculations, different buckling modes, as well as design of built-up columns. Previously, we have concentrated on W shapes, as well as square rectangular HSS sections, all without local buckling issues. Now we want to be able to adjust our buckling design strengths for local buckling. The 15th edition of the Steel Manual changes the way local buckling is accounted for the design of columns, and these provisions are given in section E7. Here, an effective area, A sub E, of the slender element is calculated, which accounts for the reduced area due to the ineffectiveness of the buckled portion of the slender element, kind of like what we do with tension members. The buckling strength of the column is then determined using the effective area instead of the gross area. Since the effective area will be less than the gross area, there will be a corresponding reduction in the buckling capacity of the column. The critical buckling stress is still calculated the same way as before. To calculate the effective area, an effective width B sub E is calculated. The thickness of the slender element remains the same. The effective width calculation is given by equation E7-3, which has a couple of terms that need further clarification. The magnitude of the effective width imperfection adjustment factors that are C sub 1 and C sub 2 are dependent on the type of shape as shown in this slide and are given in AISC table E7.1, which is given in the next slide. This slide shows the formula used to calculate C sub 2, which is a function of the value of C sub 1. Note that table E7.1 has values for both effective width imperfection adjustment factors, so that the use of equation E7-4 is really not necessary. In this slide, the formula for the elastic local buckling stress, capital F sub EL, is given. Note that its value is a function of both the slenderness ratio and the limiting slenderness ratio, as well as C sub 2. Provisions are also given for local buckling around HSS sections. We now want to re-examine the three global buckling modes for rolled shapes. We have flexural buckling about either of the principal axes, torsional buckling about the shear center, and flexural torsional buckling. How a cross-section buckles under a concentric axial load is determined by the number of planes of symmetry there are in the cross-section. There are two planes of symmetry with a W shape, one plane of symmetry with W, T, and C shapes, as well as double angle cross-sections, and no planes of symmetry for an odd shape. Table E1.1 provides a summary of the possible buckling modes for various steel shapes. Note the references to the appropriate sections in Chapter E. Note that these are all global buckling modes. All shapes may be susceptible to local buckling if any of their elements are slender enough. When dealing with buckling and axes, it's important to understand the terminology that can be used. When we say buckling about an axis, it means it is bending and rotating about that axis. It also means that it buckles or deflects into or along the opposite axis. Therefore, buckling about the y-axis is the same thing as buckling in the x-axis. Conversely, buckling about the x-axis is the same thing as buckling in the y-axis. Looking at the buckling modes for a doubly symmetric cross-section, such as a W shape, the member will globally buckle flexurally in either the principal axes, that is X or Y, or torsionally buckle about its longitudinal axis. Again, torsional buckling will not control for W shapes unless they're practically short, say 6 feet in length. For singly symmetric sections, where there's only one axis of symmetry, you have either flexural buckling about one axis and flexural torsional buckling about the other. Buckling in the plane of symmetry will be flexural buckling. For a WT shape, this is buckling in the y-axis or buckling about the x-axis. For C shapes, this is buckling in the x-axis or buckling about the y-axis. The flexural torsional buckling occurs about the plane of symmetry. For a WT shape, this is buckling in the x-axis. For C shapes, this is the y-axis. It is very important to note that flexural buckling will not occur about the plane of symmetry. If you calculate the flexural buckling strength about the axis of symmetry, which you can do, it will overestimate the design strength, which is obviously not good. The fact that the cross-section can twist as it bends out means the cross-section is less stiff, hence results in a lower buckling load. Therefore, flexural buckling does not exist about the axis of symmetry. For singly symmetric sections, such as WT and C shapes and the double Ls, a different critical buckling stress is calculated as given by AISC equation E4-3. This equation has several new terms in it. Note that if local buckling is possible, an effective area is used, just as previously discussed in this lesson. Shown in this slide are definitions of the new terms. The shear modulus, it's capital G, is related to the modulus elasticity by Poisson's ratio and has a constant value of 11,200 KSI for constructional steel. The torsional constant J is given in the shape tables for all rolled shapes. The polar radius of gyration, R bar sub naught, and the flexural constant, capital H, can be calculated by equations given in section E4. That's page 16.1-36. However, this requires you to determine the distances between the shear center and the centroid of the cross-section for each axis. You ask, what is the shear center? Well, the shear center is the location the cross-section rotates about in the longitudinal axis when twisting. It's actually much easier to obtain these values from the AISC shapes database as given in their column locations in this slide. And I believe that references version 14 of the database. In summary, singly symmetric cross-sections will buckle in the flexural torsional mode when it buckles about the plane of symmetry. It is important to note that pure flexural buckling will not occur for buckling about the plane of symmetry. If you calculate the flexural buckling stress, you will find that it is higher in magnitude than the critical buckling stress taking into account flexural torsional buckling. Therefore, ignoring the flexural torsional buckling mode is unconservative. The design capacity values in column design tables for WT and two or double angle shapes are correctly calculated for flexural torsional buckling. Because you have two different modes of buckling, you cannot properly obtain the buckling strength from the other axis using an effective length, equivalent effective length like we did with the W shapes. Buckling capacitors are therefore provided for both axes in these tables. Buckling about the y-axis is calculated based on flexural torsional buckling, while buckling about the x-axis is pure flexural buckling. Another issue with columns is the reduced buckling capacity of built-up columns. These are cross-sections that are made up of two of the same shapes. The shapes are placed back to back and are usually separated by a gap to allow for the gusset plate connection at either end of the column. Obviously, connecting the two shapes together can increase the buckling capacity beyond simply doubling the capacity of a single member. For buckling about the y-axis, as shown in the slide, a new moment of inertia and radius of gyration must be calculated using the parallel axis theorem. However, depending on the type and number of connectors between the two shapes, a reduced stiffness can occur, lowering the buckling capacity as each shape tries to slide past each other as the member buckles. It is important to note that buckling about the other axis, say the x-axis, is unaffected by connectors and will simply be double the buckling capacity of one of the shapes. Also note that in addition to the reduced stiffness, you may have to consider local buckling effects. Also, the buckling about the y-axis for double angles can involve flexural torsional buckling. It's a lot of work to do the calculations. To account for the reduced stiffness due to the connector spacing, a modified slenderness ratio is calculated by the equation given in the slide, which is equation E6-1. The result is an increase in the slenderness ratio, which reduces the buckling capacity. The more intermediate connectors used to connect the two shapes together, the lower the increase in the slenderness ratio and the higher the buckling capacity. Note that the term little a is the spacing between connectors, and R sub I is the minimum radius of gyration of a single shape, which is R sub Z for an angle. The equation shown is used when snug tight fasteners or bolts are used. When pre-tension bolts or welded connections are used, there is less slippage between the shapes and a higher buckling capacity is obtained. The modified slenderness ratio in this case is given by equation E6-2A or E6-2B. Fortunately, column design tables are provided for double angles with intermediate connectors. Tables are provided for double equal leg angles and unequal leg angles with either the long legs back to back or the short legs back to back. Note that how the angles are oriented with respect to each other will affect the calculation of the moment of inertia and the radius of gyrations. Again, due to the different buckling modes in each axis, separate design values must be given for both the x and y axes. It is important to note that the tabulated values in table 4-8 through 4-10 are for pre-tension fasteners or welded connections. The far right column indicates the number of intermediate fasteners that are needed to achieve the values reported in the table. Shown in this slide is a column design table for single angles. It turns out that the calculation of the buckling capacity of single angles can be rather complicated. This is because the axial load cannot be applied at the centroid of the cross sections like other shapes, or even a double angle cross section. Therefore, bending is introduced into the member for any non-zero load. To complicate further, flexural torsional buckling can occur about its weak axis and the z-axis. Throw in local buckling and you have a lot of calculating to do. Fortunately, There are column tables for single angles. Note that the axis of buckling is the z-axis. This ends Lesson 17 and Module 7.